Okay, so we were seeing the limitations, wherein it has no noise, uh, you know, uh, short circuit protection, and also the output voltage is fixed. There's no option of scaling in or scaling down on the output voltages. Okay, so since there's no short circuit protection, right, that becomes a little tricky to handle, right? So we have certain advantages. The best one that I was mentioning to you about is this thermal shutdown, right? But then, after the circuit, probably, the circuit protection can be enabled, which means I'm trying to say that, after the circuit here, right, we can probably include a small circuit, okay, which can actually have a fuse built in, right? So that's the only way that, we can make changes to this MC78XXC series, right? Okay. Now let's understand the performance parameters, right? So whenever we are looking into an IC or a circuit for that matter, we look into the performance, right? So if the performance is good, then yeah, we will go ahead and as mentioned previously, right, we look for more of advantages compared to disadvantage, right? Okay. So the first one that we'll be seeing is the line or input regulation. So this is defined as the percentage change of output for a change in input. So if in case some changes are done in the input side, how is it impacting the output, right? How are the changes happening on the output side? So what percentage? So that is nothing but called regulation. So if you can put that in the form of formula, right? So it becomes VHL, okay, minus VLL. Okay, so here HL is nothing but high line and LL is low line. So the load voltage with respect to high line, okay, minus low line. Okay, so this will give me the percentage of regulation with respect to input. So which means if there are some changes in the input, and how is it going to impact my output. So the second one is load regulation. First is the input regulation, and now is the load regulation. Okay, fine. So defined as the change, okay, just a moment. Yeah, so defined as the change in output voltage for a change in load current. So this is output and load current. So the first one, when we talked about input regulation, it means changes in input and output. So there's a relationship here between the input voltage and the output voltage. But then here in load regulation, changes in output voltage for a change in load current. So output voltage, load current. So towards the output side is load regulation, towards the input side is the input regulation. But then in input regulation, we are trying to relate input voltage and output voltage. But then in load regulation, it's only output voltage and the current across the load. Fine. So the typical value is about 15 millivolts, and typical value for this is about 3 volts for line or input regulation, right? So just keep that in mind. It's about 3 volts, and here it's about 15 millivolts, right? Okay. And the next thing is if we bring out in the form of formula, right? So NL, okay, no load, FL, full load. So these are the things here. So NL means no load, FL means full load. So okay, based on how much of loads, if the load is there or present or absent, so based on that, we calculate the voltages across, and without load minus full load divided by full load. So that gives me the percentage line regulation with respect to load. The third one is ripple rejection, right? So ripples are nothing but, maybe you can imagine throwing a stone on water, okay, probably a water body. So you can find this ripples, water ripples happening, right? It's like waves, small waves that keeps propagating. So here also, in our electronic devices, how does these ripple, tackled? How are these tackled, or how are these, taken into consideration, right? So since we are looking at circuits more reliable, okay, we want them to be as good as possible, right? So the regulator ICs not only keeps the output voltage constant, but also reduces the amount of ripple voltage. So regulators not only keeps constant output voltage, but then it also helps in reducing or nullifying the ripple effect. Okay, so this ripple rejection is mentioned in the form of decibels. Okay, and the values, the typical values are about 78 dB. So 3 for line input rejection, 3 volts. Load rejection, load regulation is 15 millivolts, right? And ripple rejection is about 78 dB. Okay. Now formula wise, VR out is equal to VR in divided by 1 plus A into beta. So this is nothing but A is gain, and this is the factor, gain factor beta. The ripple rejection can be expressed as RR, ripple rejection. So VR out by VR in. Okay, so output by input. So this is a IC regulator, which is used as a current source, and input is V in. It has capacitor CI. Okay, and 7805 is the IC number. Input is 1, 2, 3 is ground. Remember the 78 series, and 05 is the 5-volt output concept, right? And input minus output, so that should be about 2 volt of difference, right? So input should have greater values. We have learned about that, right? And you have current across the resistor R and current across the load RL. Okay, 10 ohms, 10 watts, 5 ohms, 5 watts. Okay, so that's about the concept with regards to the IC regulator. Now when the potentials are passing through, okay, so there is going to be a drop of about 2 volts, right? So this 2 volts is taken because it has to regulate, it has to check for the input lines, and it has to pass through. Always remember, whenever there is a wire, okay, even a millimeter increase in wire will actually increase the resistance and the capacitances, right? So now we are looking at an IC altogether, right? So in an IC, we have many transistors, okay, millions and millions of transistors. So here this IC, okay, maybe it may not have billions of transistors, it might have few transistors, but then few gates, but then these delays, these drops across each transistor will add up, and finally when it comes at the output side, right, you are finding about 2 volts of drop compared to your input side. So input side and output side, when you compare, there is about 2 volts of drop. So that's why when we are giving an input, we try and give it about 2 volts higher. If you can remember, right, we had learned about it, right? So the input should be about 7 volts, right? So Vi should be greater than or equal to V naught plus or plus 2 volts, right? So it should be a little higher. Okay, now the booster circuit. So 7805, how do we act? How do we make the 7805 act as a booster? So 7805, how is it used as a current source, capacitor, and 2 resistors at the output side, right? But then if I have to make it as a booster, right, to increase its performance, I need to take the help of a transistor Q1, right? So at the input side, now I have resistor R1, and the input along with the R1, it gets into the transistor Q1. Okay, so it just passes through, and then ground, you have I think it's connected to 3. Yeah, the third pin, 7805, the third pin, and this is going to be the first pin and the second pin input and the output, and the collector current. So which means across the load we have the collector current, and then we have the node current, and I naught is the output current from the IC 7805. Okay, so if I have to calculate, so it should be across the load, so with respect to ground. So we will see its characteristics, we will see some equations. Now the load is nothing but IC plus I naught, which I mentioned here, right? Load is nothing but IC plus I naught. So the two currents are merging here. And IC is equal to the beta, which is the gain factor. Okay, beta is gain factor, and IB. So IB is the base current. Okay, so emitter, base, collector. So three terminals of these transistor. So this is the base, is the emitter at the top, and at the bottom we have collector, right? So IC is equal to beta into IB. So beta is a gain factor. So beta is again dependent on many factors such as mu and COX and W by L, right? So when I say mu and COX, that is nothing but the permittivity concept, right? Mu is nothing but the permittivity concept, and COX is the oxide capacitance, right? Oxide capacitance, and W by L is nothing but the width and length of the transistor. Now you might be wondering, sir, what is this W by L, right? So as we know, there is a channel formation that happens, right? Once it crosses, okay, once it crosses its threshold voltage. So any transistor for that matter, it will start functioning. So after it crosses its threshold voltage, it's then on we say that the transistor is turned on. Now this W and L, okay, is nothing but the distance between the source and the drain when I'm talking about MOSFETs, right? Metal oxide semiconductor field effect transistor. So that's the difference between the source, or the gap that exists between source and drain. So similarly here, when I talk about this uh, W by L, it is talking about the width and length, the dimensions of the transistor through which we take it as the properties, just like how you uh, build your house, right? You measure how much of length, how much of width. Okay, you say 30 by 40, so that's actually referring to the width and length, right? So similarly here for the transistor, we have W by L. So I am going to check, okay, what is going to be the width of the transistor, what is going to be the length of this channel inside the transistor. So these are very minute details that you will be looking into probably in your upcoming semester, fifth semesters, and where you'll be exclusively learning on CMOS circuits, right? CMOS VLSI design, complementary metal oxide semiconductor. So there you will be studying exclusively about the W by L ratios of a transistor, right? So as of now, you can remember that the output voltage from this IC, okay, 7805, and the collector current both combines, and it appears across the IL. Now I naught is equal to input current II minus IQ. Okay, so this is approximately equal to the input current because IQ is very small. Okay, and IB is equal to II minus IR1. So the current across resistor R1. So that is IB. Okay. So if I have to calculate, so this becomes, since it's I naught is equal to II, so instead of I put it as I naught minus I is equal to V by R. So V is between the emitter and base when it's turned on, right? Remember, when it's turned on, and then divided by R1, right? Because that's the resistor we have here, R1. Okay, right. And once we simplify this equation, right? So this is what we are going to get, which is IL is equal to beta plus 1 into I naught minus beta. The same thing is here, right? VEB on divided by R1. So the maximum current that we are looking at, the output maximum for this regulator 7805. So maximum, the output voltage. Now leave about the collector current, leave about the load current. The maximum that comes out from this IC is 1 amp. Okay, so this is based on the data sheets here, right? And assuming VEB on is equal to 1 volt and beta is 15, right? uh, Now beta is also dependent on W by L ratio of the transistor, the width and length of the channel of a transistor, right? Okay, so yeah, W by L, so that gives us the beta. So we get from this equation, right, from IL is equal to beta plus 1, as IL is equal to, because this is beta plus 1, so 15 plus 1, 16, okay, into I naught, because it is 1 amp, right, minus beta again 15, okay, then BEB we're going to take as 1, and the resistor, okay, R1 is taken as 7. So if I take that into consideration, right, so I'm going to get about 13.8 amps. So that is the load current that I'm going to see. Now that load current is actually here, right? So I naught is different. IC is with respect to the transistor Q1. I naught is with respect to 7805, and IL, okay, IL is the current with respect to load. So at different points we calculate, and we are getting different values. Keep in mind, okay, I naught is 1 amp, okay, and for the load, with the given values, right, you can take this as an example even while writing the explanation for it, right? You can consider few values. You can take either the same values, or probably you can take different values, right? Beta and VB on, and the value of resistance. So take this all, and you can just calculate, and you can say that IL is going to be this much amps, right? Now, with regards to fixed regulator, okay, used as adjustable regulator, right? So how do we do it? Whenever there is an adjustable concept, right, we should always remember that there is a resistor involved, resistor, right? So wherein we can increase and decrease the value of these resistances. Now, the same thing is used here, right? The regulator 7805, right, 7805, and it's different configuration, right? So I'm using a movable resistor here, right, and I'm going to use a capacitor at the output, which is 0.1 microfarad. Important formulas to remember: V naught, output voltage, is VR, okay, so VR is here, okay, uh, plus V pot, okay, so we are taking this as pot because this is variable, okay, so V pot is equal to VR plus. So this V pot now, it has uh, currents. V is equal to IR, so this V is equal to IR here, right? So I is IQ plus IR1, okay, so the current which actually gets into R2. So IQ plus IR1 into R2, because we are calculating with respect to R2. So this is equal to VR plus IQ. I'm just multiplying them, IQ and R2 here. So IQ R2 plus R2 remains here, and VR divided by R1 R2, right? So because this IR1, okay, this IR1 again, I am trying to shift it, okay, because that is VR divided by R1, because it's with respect to resistor R1. So my final formula is going to be, as we have seen here at the bottom, right? So that's going to be the final formula. So you'll have to remember this formula. V naught is equal to 1 plus R2 divided by R1 into VR plus R2 IQ. So this is how it's calculated. Okay, so main thing that you should remember here is how these regulators are connected, right? You have variable resistors. Okay, if it's an adjustable regulator, or if not, if we are not using that, then we will be, if we are using as a booster, then we need a help of a transistor, right? And if we are using as a current source, right? So, the whole configuration changes. Here also we have these resistances, but then it's not variable, right? So capacitor and resistor at the input and output respectively. So that's a current source, right? Okay, fine. Now, about the general purpose regulator, okay, 723. So how this general purpose regulators function? So you can just imagine, um, uh, it's another type of IC, just like how we saw 7805 and various applications with respect to 7805. We have now 723. Okay, so this is question can be asked specifically. Write a short note on 723 general purpose regulator, right? And yeah, so this is the circuit here, right? So just have a look at it. Right, so you have a quite a few you know sensors here, right? You have temperature compensated zener, and you have a current source here, right? Voltage reference amplifier, and you have plus V, minus V. Okay, then you have error amplifier. So this, this is going to get the inputs here with the pin number 2 and 3, and it is just like a difference amplifier here, right? And the output is sensed, it is given to the base of the transistor. Okay, so this is nothing but a series pass transistor. So the output of error amplifier is actually driving the transistor here. Okay, and not only to the base, okay, it's also giving to the other transistor. So maybe you can call this as transistor 1 and transistor 2, right? So here I can give the current limit. Okay, so because this is driving the base of transistor, always remember this is just like the gate in a transistor. So base in this BJT, right? So as you all know, BJTs are very good in conducting currents, right? For current carrying capabilities, loads, in buffers, super buffers, we use BJTs, right? So this is going to be the frequency compensation line. Okay, and ultimately we'll be able to control how much of uh, thing is passed to the transistor. So we will see now how it actually functions. So this is the internal structure, right? Internal structure where the reference amplifier, which means I'm talking I'm talking about this here, the reference amplifier, right? And here we have error amplifier, right? So this is the reference and this is the error amplifier. So here in reference amplifier, you have the diode, okay, which means we are actually using a Zener diode, okay, and you have plus volt minus, which is as good as the op-amp, right? We are where we are giving the plus VCC minus VEE, the same concept here, right? Because it's an op-amp anyways. So you have a constant current source, then you have a Zener diode, okay, you have an op-amp here, and the final voltages that comes across, which is about approximately 7 volts, right? And the error amplifier, right, which is inverting and non-inverting. Ni is non-inverting. Okay, so the output here is driven by the two transistors I was mentioning, right? Q1 and Q2. Let's go back. right? Q1 and Q2. So it is like, this image is shifted anti-clockwise. You can see here, yeah. And you have the collector voltage and the output voltage here, right? Yeah. Okay. Similarly, you have CL, okay, and Q2. Fine. So this is the internal structure of your 723 general purpose regulator, right? So if we have to see the pin diagram, it has about 8 pins, okay, and current limit, current sense, inverting input. So all these are different inputs that we are going to give the reference, okay, minus and then plus to 7 and 12, right? Frequency compensation, where do we see that frequency compensation, right? We see here, right? Frequency compensation is at 9. Here we are using pin number 13, okay, and V out, okay, VZ. Fine. So if we have to see that here, right, if we have to see that, just it is put in a circular fashion, right? Current sense, inverting input, non-inverting, 2 3, right? 2 3, and 4 is used as a reference, right? 5. Okay. Now, how do we use this as a low voltage regulator? Okay, so V naught can be varied from 2 volts to 5 to 7 volts. So which means there is a 5 volt range between the output voltage, right? So I have an unregulated supply. As you all know, regulators are usually used to regulate the unregulated supply, right? So unregulated supply are towards the left hand side. Then you have the regulator here. Then at the output, you will get a constant output voltage, right? So so if a question is asked with regards to 723 as low voltage regulator, this is going to be a circuit diagram, right? Of course, you're going to use a block for this. Okay, so you can see the same numbers here, the negative voltage and the positive voltage, 712, right? 712. Okay, if you want, you can neglect this, right? It's not needed. You can just use the spin diagram if required. Fine. So the capacitor value is about 0.1 microfarad. Okay, then you have R1, R2, non-inverting input, right? Capacitor is connected to non-inverting input. Okay, and to the inverting input, we are actually giving a resistor and capacitor. So if you can build this, right? If you can build this using a breadboard, right? This circuit will be helpful. You can take a 723 IC, give a normal DC supply there, right? Unregulated. You can connect an oscilloscope there, towards this point with respect to ground. One probe here, one probe here, and at the output, one probe here and one with the ground. So if you connect like that, you'll be able to see the difference, between the inputs and the outputs. So coming to some equations here, right? So the output voltage is nothing but the reference voltage. Remember, we are giving a reference here, right? We reference at 6th pin. Okay, right? This becomes our reference at the output of first op-amp. Okay, so we reference into R2 divided by R1 plus R2. So R2 is here, okay, and R1 is here. So R2 divided by R1 plus R2. So V reference into. So why is it V reference? Because see here, this V reference is actually coming inside to the error amplifier, and then it is coming to the transistors here. So we have to multiply V reference here. Okay, so V reference into R2 divided by the total R1 R2. The reference voltage is typically about 7.15. Of course, we say 7 volts, but then it's about 7.15. And if we can put those values here, so the output voltage V naught is equal to 7.15 into R2 divided by R1 plus R2. So based on the question, you can decide, how your answer is going to be. Either you're going to use uh, the circuit, or probably you're just going to use the block diagram here, as mentioned, the circuit diagram, which is for low voltage, right? You can mention about the range that it can operate, the 5-volt range, right, from 2 to 7, and you can include your answers with some equations. That should be sufficient. Now, if I have to have a high voltage, right, high voltage, so the circuit changes, but not drastically, right? Just have a look at it. So as I was mentioning, there's just a slight change in the circuit, right? We'll just go back. Yeah. So we have R1, R2 connected, but then you can see for high voltage, okay? So this resistor is just connected here, and we do not have a capacitor at the input side. Okay, so between 6 and pin 5. See, between 6 and pin 5, we had only R1 here, and then we had R2 and capacitor in parallel. But then here we have removed these two, R2 and capacitor, and we have just retained the single resistor. Okay, so as usual, we give the negative potentials here, the positive potentials here. Unregulated supply is given to the non-inverting terminal. Okay, this capacitor is retained, right? You can see this capacitor is retained along with the resistor. So we had that resistor combination here towards the input, but now we have that combination towards the output side. R1, R2, it is shifted towards the output side. Just compare, see, R1 and R2. So I am shifting this here, and this R3 is coming here, right? So we are swapping out the resistors, but then this capacitor is left out. Okay, fine. So my voltage gain is 1 plus R1 divided by R2. So it should be always more than unity. Okay, more than unity, because it has transistors involved. So we are just taking it as 7.15 into 1 plus R1 by R2. So V0 is equal to V reference into AV, right? So the same formula here, V reference into AV. Okay, so yeah. So this is going to give me an output voltage which is much greater than 7 volts, right? So if I want between some low voltage, so some low voltage application, maybe some small LED that you want to glow or something, so you can go with this circuit here, right? Maybe if you want something bigger, okay, then you can actually go with this circuit, which can deal with more than 7 volts. Okay, fine. Now, based on the pulse width, remember I was telling you about the pulse width, when the on period and off period, how it changes, right? So accordingly, we can actually increase or decrease the speeds, right? So this is what I have put up here, right? So you can see that the on time and off time both are equal, 50-50, right? It is on for 50% of the time and off for 50% of the time. And the highest voltage that it's attaining is about 10 volts and averaging it at about 5 volts, lowest being 0. Now, if I want on time to be at 25, so off time will be for 75% of the time, right? And I can invert it as well, right? So I can bring it to 7.5 this side, and 25% it is off. So which means you can see when it is 50-50, when it's on and off, okay, the average value that it can reach is about 5 volts. And then when the on period is about 25% on time, so it's 2.5 volts. When we're giving about 75% of this width, okay, then it is reaching 7.5. So you can notice the changes happening, right? The voltage levels that it can reach based on this width of the pulse, right? So this is an important concept with regards to pulse width modulation. Okay. So this is the importance, of using a pulse width modulation. Based on the on and off time, we can change the level of voltages that it can reach. Okay, so I hope you have understood, this concept of pulse width modulation. So 50-50%, 5 volts, and 25% on 2.5 volts, and 75% on is, it's reaching at about 7.5 volts. So if I keep it on continuously, then it would reach maximum of 10 volts. So this regulator is such important concept. Of course, this is not going to be asked, but then I thought, let me just include it. Okay, so this is how a switched mode power supply is going to look. Okay, SMPS. I think you would have heard of the term SMPS, very commonly, but then probably you wouldn't have known, the complexity involved in them. Have you all learned about or heard about SMPS? Yeah. Have you come across the term SMPS? This used to be a very regular term, when desktops were used, those days when there were no laptops much, right? So SMPS used to be, very much important switched mode power supply. Okay, have you heard this SMPS? Have you come across?
Yes, sir. We
Yeah.
had UPS also, like small.
Yeah.
Yes.
Okay. So this switched mode power supply, there's a lot of complexity involved in where you can see that, the AC input is there, and then you have the full wave rectifier here. These are 4 diodes, right? So which means rectification is happening at the positive cycle and at the negative cycle of the sine wave, right? And then you find here a transformer, right? And you have diodes D1 and D2. For current boosting, we have transistors Q1 and Q2, right? So reference voltage regulator. So based on how much of voltage I need, right, I can keep that as a reference, as a knob. Probably you can think of as a knob, right? Yeah, pretty interesting concepts, actually. And then flip-flops, and then oscilloscope, the oscillator, sorry, which has a frequency of about 40 kilohertz, right? And you have a flip-flop here, right? So flip-flop, as you all know, is the basic element of memory, right? So yeah, so that is one thing. And this whole thing, actually becomes the steering logic circuit, right? So it has AND gate, okay, A1, A2. So that is AND gate 1, AND gate 2, and flip-flops having 2 outputs here, right, which is Q and Q bar. So, Q and Q bar will be opposite to each other, right? And then PWM, we learned about PWM, which is pulse width modulator, right? So we're using an op-amp for that purpose. Okay, then we have a triangular waveform generator, 40 kilohertz. The voltage comparison amplifier. Okay, so this is done for error control, right? Rectification. So a pretty complex circuit which has almost everything. And then here you have your output rectifier or the filter, right? So we can design based on the values of capacitor and resistor. We can design what kind of filter it's going to be. We have seen pass band, okay, band stop, high pass, low pass. So based on the values of R's and C's, we can actually design the filter, and the final DC output voltage is coming here at the output side. Fine. So we can actually take a lot of waveforms, and I have put up here as A, B, C, D, right? So waveforms can be generated, and you can see here how these waveforms are. For example, A is referring to the triangular wave, right? So here we are giving the triangular waveform for the pulse width modulator, right? So the triangular waveform is given, and the PWM's output, right? So I can vary or I can change Now you can just see here when it's 40 kilohertz, right? So how the on and off time changes. So when it's 20, right? So that becomes the 40 kilohertz, which means higher frequency, which means more waves in the same time, right? So when I say 20, then it becomes double of this. So which means the waveform between on and off here, right, is only on here. So the frequency is less. So as the frequency becomes low, you can find that probably if I now make it 10 kilohertz, right? Let me just annotate 1 minute. Yeah. So if I make it now 10 kilohertz, okay, so this will be for a long time, and then this will be off and then on, right? So that's how it's going to be if it's a 10, right? So as the frequency reduces, right, so you can see there will be a change in the waveform. And then similarly, you are able to see the drive for Q1, okay, so which is nothing but it is referred with F, right? So this is the drive for Q1. So this is the output of AND gate. Okay, so what are the signals which are multiplied? Okay, the one is taken from the flip-flop, and the other one is actually from PWM. So when you multiply them, okay, from the PWM, so from the PWM, and the other one we are taking from the flip-flop, right? So flip-flop's point is D. So D into B. So D into B is actually going to give me F. Okay, so D is here. Okay, D into B is actually giving me F. So you can see at this point when it's on, right? So here it's off at this point, so it's off, right? So I think you're able to understand it, isn't it? Right, just a moment. Right, you're able to understand, right?
Yes, sir.
Let me just put a line so that, yeah, so D and B, right? Let me bring this down. Yeah, so we are multiplying this here, right? B and D, right? So that is giving us F. Fine. So high, it's giving me high. Okay, low, so it's giving me low. So it's basically an AND gate. So similarly, you can just compare the waveforms for Q2. Okay, what kind of waveform it's going to get. Then the switched waveform, okay, with regards to the transformer. Remember the transformer which we had previously, right? Let me just show you that here. Just a moment. Yeah, this transformer here, H, I, right? So H is here and then I is here, right? So based on the on and off time. So pretty interesting concepts, right? With regards to the voltage regulators. Okay, so I think we will end our session here. Okay, and maybe in our upcoming class we will look into 555 timers and phase lock loop and DACs.